edge chipping and stone impact damage are among the most frequent customer-observed mechanical defects, particularly on lower panels, such as rocker panels, wheel arches, and front bumper edges. From an OEM standpoint, these failures are predictable because they occur where coatings are exposed to concentrated mechanical energy, high-velocity particulates, and complex geometry. Understanding the interplay between film thickness, coating hardness, substrate support, and additive design is critical to preventing these defects. Mechanically induced failures begin at the surface, but propagate depending on the structural and chemical integrity of the coating system. When a small stone or road debris impacts the panel, the coating experiences a high localized force. If the clear coat and base coat layers are too brittle, thin, or poorly supported by the primer, the polymer network cannot absorb the energy, resulting in microfractures that rapidly evolve into chipping. Even when the top coat remains intact initially, repeated impacts weaken the polymer chains in localized zones, leading to cumulative damage. Film build is a primary determinant of resistance. OEM specifications carefully control total film thickness, balancing aesthetic requirements with mechanical durability. Thinner films may look glossy, but lack sufficient mass to absorb energy without cracking. Uneven film distribution along edges and corners, caused by spray pattern limitations or operator variation, creates stress concentrators where chips preferentially form. Overspraying to increase thickness is also detrimental because excessive build increases internal stress and brittleness, making the film more susceptible to impact-induced fracture. Cure and crosslink density significantly influence impact resistance. High crosslink density improves chemical and MAR resistance, but reduces elongation, rendering the coating brittle under point impacts. Low crosslink density coatings are more flexible, but can deform permanently, trapping debris and reducing gloss. OEM formulations are optimized to balance hardness, elongation, and stress relief to resist both stone impact and cumulative mechanical fatigue. Additives play a role in mechanical resilience. Elastomeric modifiers increase elongation and energy absorption, reducing chipping under impact. Stress relief additives help minimize residual shrinkage, lowering the likelihood of microcrack initiation. Flow and leveling agents indirectly influence impact resistance by ensuring uniform coverage and minimizing local thin spots that can act as fracture initiation sites. However, additives cannot fully compensate for poor film build or inadequate substrate support. Substrate support and geometry are crucial. Lower panels often experience more flexing due to chassis dynamics and road vibrations. Panels made of thinner steel or aluminum experience higher deflection under load, increasing the effective tensile stress on the coating. Weld seams, hem flanges, and complex geometries amplify these effects, creating predictable chipping zones. OEM engineers conduct finite element simulations and real-world testing to identify high-risk areas and validate coating performance under mechanical loading. Environmental exposure exacerbates damage. Water, sand, salts, and small debris not only impact the coating, but also exploit microcracks and thin spots to penetrate deeper into the coating system. Repeated freeze-thaw cycles and thermal expansion further weaken polymer networks, making them more prone to chipping during stone impact. Lower panels, splash zones, and wheel arches are therefore most vulnerable. Detection of edge chipping and stone impact is primarily visual, but high-resolution gloss mapping and microscopy can reveal early microfracture zones before visible loss of material. Pattern analysis provides insight into the root cause. Linear chips along edges often indicate geometric stress and spray pattern issues, while isolated impact points suggest external mechanical events. From a troubleshooting perspective, OEM engineers focus on 4 key variables: film build and uniformity, crosslink density and cure, additive strategy, and panel support. Solutions may involve optimizing spray parameters, adjusting primer and base coat thickness, modifying bake profiles, or selecting elastomeric modifiers to improve energy absorption. Process controls are essential to ensure repeatable protection across all vehicles in the production line. Edge chipping and stone impact failures highlight the dynamic nature of automotive coatings. They are not merely surface problems. They reflect the interplay between coating chemistry, mechanical design, application process, and real-world environmental exposure. Properly engineered systems balance hardness, flexibility, and film thickness to ensure resistance to impact, while maintaining aesthetic performance and durability over the vehicle's life. If you've observed chipping, cracking, or material loss along lower panels or edges, leave your questions in the comments. Upcoming episodes will continue exploring mechanical, environmental, and aging-induced failures using OEM-level diagnostics and preventive strategies.